Alright, the Chapter 1 sample test starts off like this. And again, in case you didn't already hear this, 7 times, the actual real deal test is going to follow, the same format, the same types of questions as this sample test. So in other words, this sample test gives you an excellent idea of what kinds of questions you have to be ready for, because the sample test, and again, even in more, another way to say it, really, another one, is that the sample test is like just another version of the real test. So it starts off like this, and you have to check off the boxes of like which sets of numbers does each number belong. Like, does -4 belong in the natural number set? Is it a whole number maybe as well? Is it an integer, or maybe it's rational, or maybe it's irrational? And remember, just like we did on notes and quizzes maybe and stuff like that, you can check more than one box. Okay? So this is mainly a matter of vocabulary, and so you got to remember like what it means to be a natural number. Like, what are all the natural numbers? What are all the whole numbers? What are all the integers? Etc. And I hope at this point you've already sort of got it down and understood that there is a lot of overlap in these sets of numbers. In other words, you can belong to more than one set. So -4, is it natural? No, because the natural numbers are just like the counting numbers. So if you want to make little notes, if you have to, like additional notes here on like what's basically the ultimate study guide here, like your final, study guide, not really just a practice exam. You can also think of it as like a study guide. So the natural numbers are the counting numbers, right? 1, 2, 3, 4, 5, so on and so forth. Is -4 a whole number? No, because the whole numbers are all of the natural numbers, but then also 0. All the natural numbers are also whole numbers, but also 0. So is -4 an integer? Yeah, because the integers are, all of the counting numbers and their opposites. So like 1 as well as -1, they're integers, and also 0. 2 and as well as -2 are integers, -5, -6, -7, -8, and so on. But also, 6, +6, +7, +8, +9. Those are all the integers. And is -4 rational? Yes, because if the number can be written as a fraction, okay, then you could think of it as rational. And of course, -4 could be written as or identified as or represented as -4 over 1, which is a fraction. -4 over 1. So might be good to write down some of these things that I'm saying as we go. Like -4 over 1. Another way you can think of, whether a number is rational or not. Okay, another way to sort of tell is a rational number will have a decimal that either ends at some point, or at the very least, if it goes on forever, it has to go on forever in a pattern. And -4 is basically like -4.0, like the decimal ends, or 0.0000, whatever. I mean, it's a rational number because the decimal either ends and terminates or repeats forever in a pattern. Now, an irrational number, if a number is rational, it can't be irrational at the same time. As far as rational and irrational goes, it's one or the other. So an irrational number is like completely the opposite of a rational number. An irrational number cannot be written as a nice fraction. And as far as the decimal goes, any irrational number will have a decimal that goes on forever without a pattern. It's got a completely random, crazy, irrational sort of decimal that goes on forever. So -4 can be labeled in the integer group as well as rational. And essentially, if a number is an integer, it's automatically rational. Anyway, we'll hear more of that as we go here. So 0.29. If you remember what all these vocabulary words or what sets of numbers these all represent, 0.29 is not it's not natural. Sorry, it's not natural. It's not a whole number. It's not an integer. Because remember, integers are nice. They can be negative, but they're nice numbers, integers. Rational. It is rational because it's a decimal that ends after 2 places, 0.29. And remember, it's either one or the other. It can't be irrational. 8. 8 is a natural number because it's a counting number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and it goes on forever. It is a whole number, and it is an integer, and it is rational. Okay? It's a whole number, it's an integer, and it's rational. And you'll hopefully that makes sense to you how when I say if a number is in the natural set, it's automatically in the whole number set, and therefore automatically in the integer set, and therefore automatically in the rational set. And then here we go. The square root of 5. There's your example of a number that can only be labeled as irrational. It's definitely not natural. It's not one of the counting numbers, and then it's not a whole number. It's not like 0 or a natural number. It's not an integer, and it's not rational. So now it's like, is it rational or is it irrational? Well, remember, when you think about the decimal, the square root of 5, like if you looked at your calculator to sort of double check or something, or maybe you should just know this, that a square root of 5, that decimal will go on forever without any pattern to the numbers whatsoever. It's just kind of like random numbers, one after the other. And that's what an irrational number is. Remember, irrational numbers, pretty much the numbers that make up that set, are a lot of square roots. Not every square root, right? Not every square root. Case in point, the square root of 16. Square root of 16 is not, that's rational rather than irrational. But so that's why I say a lot of square roots are in this set, as well as numbers like pi and stuff like that. But moving on, number 5, different directions. Evaluate each expression. So what is the value of all of this if you know that x is actually equal to -3, and you can just basically replace or substitute the -3 in for x, and the y, or the y's, I guess, there's 2 of them, are basically equal to 4, and you can like replace each of these y's with a 4. So that's the first, well, you know what? Hopefully I'm not muddying the water here too much, but what you could have done first here, what I did first here, it looks like, is distribute the negative. Whatever. You also could have done as your first step, plugging in these numbers for x and y. But either way, so what I did here was I distributed this negative, okay? And then I probably replaced the x with a -3 and the y's with a 4. But what you could have done, like I said, sorry to repeat myself too much here, but you could have plugged in first and then just kind of followed order of operations. So if you already did this problem and you never at any point did the distributive property here, then that's okay. It's not like you had to. But no matter what, following order of operations, as well as like proper, plugging in and stuff and keeping track of your negatives and whatnot, you should end up with a final answer of 4, no matter what your path was, and no matter what you did first or second or third, the final answer should have been 4. And when I made this key, I probably didn't have these spaces for answers, so you'd put this final answer of 4 in the space for the answer. Please keep this in mind, that number 6 has the same directions as number 5, meaning you're going to be plugging in these same values for x and y in number 6. So you're plugging in the 4 for the y and -3 in for x. And so that gets you to this step. And then here's what you might want to write down. Okay, one of the big keys here is that you want to do all of this math inside each absolute value symbols. Okay, so you would get this down to like one number, and you would get this down to like one number, and then you would actually take the absolute value. Don't do it like at all before, okay? Like don't do it before that. Like don't take the absolute value of whatever you think is going on with these. No. Get this all down to one number. See, like I'm not going to take the absolute value yet. I did 3 times -3 to make a -9, and now I'm going to do 5 minus 9. See, I still haven't taken the absolute value yet. But now that I got it down to only like one number in each absolute value, now it's time. So the absolute value of -4 is going to be just 4. And the absolute value of -3, that's going to be 3. Remember, absolute value of a number is defined as like its distance from 0 on a number line. But what that really amounts to is like you take the absolute value of a number, and if it's already positive, great, then it's just that number. But if the number is negative, you just kind of like make it positive. In other words, the absolute value of 7 is just 7. Okay, but the absolute value of -7 is also 7. It makes a number positive if it's not already positive. And then speaking of 7, that's the final answer, which you should put in the answer space. New set of directions, new type of problem. We're going to simplify each expression and square root. That'll be on the next problem. But we're going to simplify this expression. Sorry, okay? And what this is going to amount to is like combining like terms, but, and this is something I want to write down if you think it'll help as a little note here to study, you're not going to combine like terms until after you clear any bubbles that are in there. So the first thing you would do here before you would look to like terms is you would distribute to clear these bubbles. So we would be distributing this +2, and we would be distributing this -4. That's right, I said -4. So we do the distributive property, and we get to here. 2 times x squared, of course that's just 2x squared. 2 times 3x, you get you 6x. -4 times x squared, of course just -4x squared. -4 times a -x. -4 times a -x is positive 4x. And then these other two terms that are just their own like separate terms here, like not really attached to anything, they just drop down. And now that you have like 1, 2, 3, 4, 5, 6 like separate terms, now you're going to like look to see like which ones can combine together because they are like terms. So 2x squared can combine with this negative 4x squared, and it'll also combine with this negative x squared. And so ultimately, 2 minus 4 is negative 2, and then another like negative 1. Remember, people, there's like an invisible negative 1, or I guess the 1 would be the invisible part, I guess. But so 2 minus 4 minus 1 gets you negative 3. Okay? And then the other terms that can combine are the 6x with the 4x. That gets you 10x. But then you also have this 3x, which at the end of the day is 13x. And so this is the final answer. This is all you can do with it, okay? Lock. Alrighty? And then it's kind of the same directions of simplify. Simplify each square root, okay? So right here there's going to be two different methods. You probably have one of these that you're more fond of. This one I think would be like the one I'm fond of, because with square roots, remember that one of the big properties, one of the big true things about square roots is that you can multiply square roots together. If you have like the square root of 7 times the square root of 5, you can actually bring those together, multiplying, and just say that's the square root of 35. Okay, but, and because of that, you can actually break up square roots in the same manner, like kind of reverse engineer it, you know what I mean? So here's the one strategy that I like. You take a look at this square root of 18. The square root of 18 is obviously not like super pretty. It's not like you're taking the square root of 16 or the square root of 9 or the square root of 49 or the square root of 81, okay, or the square root of 100 or the square root of 4. It's not super clean. Okay, so the square root of 18 can't be done like super clean, but if you can break off a square root that can be done clean, that's going to be your way to actually like break it down and simplify it and at least take the square root of something. So the square root of 18, I could in theory don't write this down, but I could in theory say it's the square root of 6 times the square root of 3. That's true, but breaking it up like that doesn't get me anywhere because I cannot take the square root of 6 cleanly and I cannot take the square root of 3 cleanly. So I'm going to break it up as like the square root of 9 times the square root of 2, and that's going to get me somewhere because the square root of 9 is just 3. The square root of 9 is just 3. Now the square root of 2 just has to remain the square root of 2. Remember, we're only going to do like as much square rooting as we can because we're just like simplifying it. Like we can't do the entire square root of 18. So yeah, like we could do the square root of 9, but we can't do the square root of 2, and so it kind of stays like that for our final answer, and that's as much as we can do. Okay, and on a side note, when you're doing it this way, my big time advice and what you want to keep in mind is that you want to always find the largest perfect square to break off. And an example of that is if I'm doing like the square root of 48, okay, square root of 48, I could, without being wrong, I could break this up as like the square root of 4 times the square root of 12 because, hey, I can do that. I can do the square root of 4. But 4 is not the largest perfect square that I can break off of 48. The largest one is 16. So if I wanted to like get it all done in one step, you want to find the largest perfect square you can. And so this would end up being a 4, and this would have to remain the square root of 3. So that would be the final answer for like this problem. But anyway, getting back to this number 8, the other method which you might like maybe you've had Mr. Burchanowski as your teacher or something. Here's the other strategy. You can like kind of, if you know this method, then you know this method. I don't think I need to explain it thoroughly again. It's just the one where like you're breaking it down all the way into like the prime factors, and then you're finding the pairs. Well, maybe I am explaining it all the way through, but so here we had a pair of 3's, and so when you have a pair of 3's, for example, you bring 1 3 outside the square root, and then any loner numbers without any friends, like this 2 right here, would stay underneath the square root. So either way, obviously you see here that no matter what strategy you pick, you end up with 3 times the square root of 2 as your final answer. Then we sort of change gears again, and now it looks like we're getting into the world of like equations and inequalities. And so it's very important to kind of recognize, like what category, what pigeonhole or whatever that each one of these kind of fits in. You know what I mean? Like what kind of peg, or yeah, you know what I mean. Because in other words, for example, number 9 is just like a very simple equation where you're going to, it's got an equal sign, so it's an equation, equal sign. It's not like number 12 where it's an inequality because it's got like a less than sign. So number 9's, it starts off as just like a very simple equation where there's going to be like probably just one answer for x. Okay, and then you just got to solve for x. So here, remember, if there are parentheses, if there's bubbles, you're going to want to clear those first by distributing, in this case, distributing the 2. 2 times x is 2x. 2 times positive 4, positive 8. Everything else drops down. And now you can look at this and go, there's no like terms that are already on the same side of the equal sign. It's not like I have x, like an x variable on both sides. It's just I see one x variable right here. So you can work on, getting that x all by itself. Like let's get rid of this plus 8. Let's cancel out the plus 8 by subtracting 8. Of course, if you subtract 8 from this side of the equal sign, you also have to subtract 8 from the other side, to keep it balanced, to keep everything equal, to keep the left side actually still equal to the right side. You got to subtract 8 from both sides. And so that leaves you with a 2x over here. And over here, it leaves you with a 0. And that's okay. That's normal, That's allowed. You can have like a 0 over here. You just kind of keep on rocking here with your steps. So we still have to get x by itself. X is not all by itself yet. We got this 2 sticking to it, so it's 2 times x. And so to get rid of that 2, we divide. We divide both sides by 2. And again, look, 0 divided by 2 is 0. So the final answer to number 9 here was x equals 0. Number 10 is sort of the same category, but a little more complicated because it looks like there's going to be x's on both sides. So just another like little wrinkle. You still have to clear bubbles first. Like that would be pretty much always your first priority, is clearing parentheses, usually with the distributive property. So distribute the 4 with multiplication, distribute the 2, and that's what you get. And then, before you can really get down to getting the x by itself, you have to sort of get the x's only on one side and combine them together. So it looks like here I decided to subtract 18x from both sides. What that would do is get, move this x term away from the right side and gather them together over here on the left. So in order to get rid of an 18x over here, I subtracted 18x. Now, if what you did, hold on, if what you did was subtracted 4x from both sides, and you ended up with your x's together over here, that is fine. That's totally fine. In fact, based on what we decided to sort of, emphasize in class, maybe that's what we emphasized in class, is keeping it positive, right? Because you see how I ended up with a negative 14x. It's very possible that in class that we sort of decided, as a consensus to avoid negatives, which and to do that again, you would instead subtract 4x from both sides. Whatever, it doesn't matter. Because once you get the x's only on one side, now you can work on getting that x all by itself. And so here I would subtract 20 from both sides in order to leave negative 14x left over on the left side. Well, maybe I'll... So what's going to remain is negative 14x on the left side. The right side becomes negative 28. And then you do the move of dividing both sides by negative 14 to clear that out of there. Remember, you always do the opposite to get it out of there. And so you find, once you get x by itself, it ends up being x equals 2. Number 11. Number 11 is a different sort of solving in a way, because you have a lot of different variables. Here you have a v variable, and you have a r variable, and you have an h variable. This pi, you probably know, is not actually a variable. It's literally a certain number. But so it would have been basically the same situation if this pi was just like a 7 or a negative 12 or something. But what you want to do here in this problem is solve for h. In other words, that just means get h by itself. Because at first, the v is by itself. The v variable is by itself. We want to just move things around in the equation and end up with h by itself in a very similar way that we ended up getting x by itself here. It's just we're just not going to end up with a cute final specific answer. We're not going to end up with h equals 9. That's not the kind of answer we're going to have, but at the same time, we are just, again, getting the h by itself. So we have to get this pi r squared just away from the h. And in this case, what we do is we divide both sides by the pi r squared, and that is what's going to kind of cancel out, because it was pi times r squared times h. So in order to get rid of this stuff, we divide both sides by pi r squared. And so what does the left side become? What the heck is v divided by pi r squared? Well, it's v divided by pi. I told you, you're not going to end up with a cute final answer. This is actually what the final answer is. So that's probably the biggest mental hurdle to get over, is just remembering that, yeah, this is what our final answer looks like. H equals v all over pi r squared. And then we get into some inequalities, which is very similar, solving for x, right? Remember, and this is something you might want to write down, okay? The only big difference is when you're solving an inequality compared to solving an equation. With inequalities, you potentially would have to flip the symbol. Do you remember when you'd have to flip the symbol on your way to solving for x? Hopefully you remember that if you ever find yourself dividing both sides by a negative or multiplying both sides by a negative number on your way to getting x by itself, you would have to flip the symbol. A less than would become a greater than would become a less than, whatever. The other difference is that with inequalities, you normally end up with infinitely many answers, which sort of what's the word? Sort of is kind of coincides with having a graph. You can represent your answer in the form of a graph, because there's not technically just one answer. Like here, case in point. Again, you solve for x, solve for x, solve for x, solve for x. We never divided by anything negative on both sides. We never multiplied both sides by something negative. So we got x by itself, and it was x is less than 5. So what I was saying was, technically, this represents, an infinite number of answers. It's not x equals 5, it's x is less than 5. And, that opens up the, the possibility of showing your answer in the form of a graph on a number line. And so here, going into this exam, you got to remember that with a less than symbol, you would leave your circle here open. If it was less than or equal to 5, you would have had a closed circle. Write that down as a reminder if you need to. Okay, how when do you use a solid filled in circle, and when do you use an open circle? Sorry, you probably know that sound all too well. And then, obviously all the numbers that are less than 5 are to the left of 5. Number 13. Again, this fits the category of, two inequalities at the same time, which is often called a compound inequality. Now, the good news here is, oftentimes with the word or, if the two inequalities are kind of joined and connected by the word or, they're already going to be two completely separate inequalities. So all you have to do here, and again, write this down if you want to, is just solve each one separately for x. Graph them both, and don't be surprised, that the graphs run away from each other. I mean, look, x is less than or equal to negative 5. That's this graph. Again, solid circle. Or this one, x is greater than or equal to 3. Remember, since it was greater than or equal to, so it's going this way. And again, you probably heard me say this in class, when the word is or, 98% of the time, when the word is or, the graphs are going to be going away from each other. Like two oars in the water, looks like. Number 14, we get into some absolute value. So an absolute value equation. So it's an equation, it's got some absolute value, it's got the x in there, So remember, the first step is to get the absolute value part by itself, not x. You're not getting x by itself at this point. What you're doing is you're getting the absolute value part by itself. Okay, like you're getting the absolute value of x plus 3 by itself. So the first thing we do is we get this minus 4 out of there by adding 4. And then we're going to get this 2 out of there. Don't distribute, okay? Again, we got the first step overall, really, the first couple of steps, the first step or couple of steps is so that you can get the absolute value part by itself. That's what you're doing. So when you follow that step, that doesn't mean you're going to be distributing the 2. It means you're going to be dividing by 2 to get that 2 out of there, so that the absolute value part is now by itself. From there, once you get done with that, which sometimes you don't even need to do any of that at all, case in point, but once you're here, okay, now you can break this up into its 2 cases, right? Like Mr. Birchanowski says, 2 vertical lines that mean absolute value. If there's 2 vertical lines, there's 2 cases. Case number 1, where the x plus 3 can be equal to positive 5. And then case number 2, where the x plus 3 can be equal to negative 5. So you break it up into your 2 cases as you drop the absolute value, okay, lines. And now you have 2 equations that you solve separately for x. Okay, now it's like elementary at this point. Solve each one for x, and you have your 2, count them, 2 answers. So x could equal 2, or x could equal negative 8. You have 2 solutions to that equation. It's a very, 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 very similar strategy for, if it's not an equal sign, instead it's an inequality. In this case it's a less than. Okay, so again, if this needs to be isolated by itself, you would do that first. But guess what? It already is. The only thing over here on the left side is the absolute value part of 3x minus 6. So we go ahead and we break it up into its 2 cases. Case number 1, pretty much as is. You didn't really change anything except, of course, dropping the absolute value symbols. Now, the second case, all right, you're going to be making some changes. But first of all, the proper word is and. And remember, like this is where you can say like, more than or, less than and, less than and. If it would have been a greater than, more than, then the word that would have fit the situation would have been or. So again, first of all, the word that technically fits here is and, but then again, people, the graph is going to reveal that anyway. So, the cat's going to be out of the bag with the graph that the word that fits here is and. But anyway, the other case, remember, the first case didn't really change anything, except again, of course, dropping the absolute value. But the other case, do you remember the changes? You have to actually make 2 changes. The symbol needs to flip, so the symbol becomes greater than, and the 12 becomes a negative 12. So there's the split. There's the 2 cases. This 3x minus 6 is going to be less than 12 and greater than negative 12. And now that you have 2 separate inequalities, just like before, you solve them both for x. Over here, you're going to add 6 to both sides. Oh, I guess in both cases, add 6 to both sides. And then you would divide both sides by 3. You're going to graph both of these on the same number line. And since the word is and, or, well, since the graphs are running into each other, they just kind of collide and join together. And you only kind of go with the overlap, so you just kind of let them join together. And this is what your final graph would look like, because greater than negative 2, this one's going this way, less than 6, so this one's going this way. And you just let them collide and join together and like kind of stop as they join, okay? And that's it. So again, your actual test is going to be very, very, very much like these 15 problems. So, happy studying.